Hi everyone, we are from Group 3. So today we are going to talk about Taylor's method. So now I'm going to introduce my group members. The first one, Sanjay Raj. Matrix number 228450. The second one, K. Razi bin Muhammad Sabah. Matrix number 227477. The third one, Tai Yi Chen. Matrix number 228699. And the last one, which is me, Wei Yao. My matrix number is 230480. So this is the learning outcomes of our presentation. First, we will explain the purpose and concepts of Taylor's method. Second, we will discuss the algorithm and the steps involved. And the last one, we will present two examples in real applications that use Taylor's method to solve the problems involved.
Hello everyone. So today I'll be explaining on the purpose and also the concept of Taylor method along with a simple flowchart of how it works. So let me begin with the concept of Taylor method. So Taylor method is a mathematical way to represent a function as an infinite sum of them. This method helps us to approximate a complex function using their derivative at a specific point. It is especially useful when working with a function that are difficult to solve analytically. As you can see on the formula you see on the screen, it shows how a function can be expanded using a derivative, starting from the function's value, followed with the first derivative, second derivative, and also the third derivative, where n is the number of times the function is being differentiated, and f to the power of n is the n derivative of the function. So this method was named after Brooke Taylor, an 18th century mathematician who introduced this powerful technique. Now let's move on the purpose, where Taylor method is mainly used to solve ordinary differential equation (ODEs), where an exact solution is difficult to find or impossible to find. This method help in simplifying complex differential equation using their series expansion, solving ODEs numerically, analyzing system in engineering, physics, and applied sciences, and also simulating a world problem, real world problem like a population growth, electrical circuits, and motion dynamics. So in short, Taylor method is very practical and widely used in a various scientific fields. Finally, let's look at the flowchart of the Taylor method. It began with a differential equation of the form of dy over dx equivalent to f open bracket x and y, and also the initial value of y x naught equals to y naught. The next step is we have to choose the step size and also to compute the necessary derivatives at a starting point. After that, we can apply the Taylor expansion as you can see on the screen that we highlighted in a pink color to estimate the value of y at the next point. X1 is equivalent to the x naught plus h, the one we highlighted in the yellow color. So this process is repeated step by step to find values over a given range. In conclusion, Taylor method is a valuable tool for approximating solution and also modeling a complex system effectively. Thank you. That's all for me.
So this question will be an example that I use to explain and discuss the algorithm and step involved in the Taylor methods. So throughout the questions, the key information that I can obtain is first one, dy dx is equals to x plus y. The second one, y0 is equals to 1, which means that y is equals to 1, x is equals to 0. The third one, second order Taylor methods, which will mainly use to identify which formula that we need to use based on the general formula. The fourth one, h is equals to 0.1. So after obtaining all the key informations, we have come to the solution parts. Step 1, derivative. dy dx is equals to x plus y, which is given in the questions. So in this step 1, what we need to do is we have to differentiate dy dx to get d2y dx2. So the result in the step 1 is dy dx is equals to x plus y, and d2y dx2 is equals to 1 plus bracket x plus y. So in the step 2, we have to let x0 is equals to 0 and y0 is equals to 1, which is given in questions 2. So after obtaining the x and y from the questions, we have to substitute them into the formula that we get obtained in the step 1. So what's the result of step 2? dy dx is equals to 1. d2y dx2 is equals to 2. So that's the result that we obtain from the step 2. In step 3, we need to find y1. The formula of y1 is basically based on the general formula and the third key information that we obtain from the questions. which is the second order of Taylor methods. So y1 is equals to y0 plus h dy dx plus h squared d2y dx2 over 2. And then we need to substitute h is equals to 0.1, y0 is equals to 1, dy dx is equals to 1, d2y dx2 is equals to 2 into the formula. All these informations and value can be obtained or find in the questions or in the step 2. So after the calculations, we'll get the y1 is equals to 1.11. So now, step 4. We let x1 is equals to 0.1 and y1 is equals to 1.11. Then we substitute these values into the dy dx and d2y dx2 formula. And finally, we will get 1.21 and 2.21. Basically, the steps 4 is actually same with the step 2, which is the substitution of x and y into dy dx and d2y dx2. And we'll get the values. So one question before I end the step 4. Why x1 is equals to 0.1? x1 is equals to 0.1 because x1 is equals to x0 plus h. x0 is 0 and h is 0.1. So x1 is equals to 0 plus 0.1. So x1 is equals to 0.1. In step 5, we are going to repeat the same solution in step 3. So in step 5, we are going to find y2. So to find y2, we have to substitute y1 is equals to 1.11, h is equals to 0.1, dy dx is equals to 1.21, d2y dx2 is equals to 2.21 into the y2 formula. So after the calculations, we will get y2 is equals to 1.24205.
Okay, let's move to our first example. Before we start trying to solve this question, let we find out why is this question suits to use Taylor series. First thing first, it was indeterminate form in limit, and then functions are easily expandable, and then it has accurate approximate, which is near x to x equals to 0, and then no elementary antiderivative. Last but not least, simplifies complex expressions. Now, we are on how to solve this question. First thing first, we need to evaluate each limit using Taylor series. We will evaluate the limit of cos 2x minus 1 divided by x squared times exponent power of x. First step, we need to find the Taylor series expansion of cos 2x. Now, we assume cos 2x as cos u. By using the Maclaurin series, we got cos u equals to 1 minus u squared divided by 2 factorial plus u power of 4 divided by 4 factorial and so on. And then we substitute u back to the 2x. For small x, we can approximate cos 2x using the first two terms, which is cos 2x equals to 1 minus 2x squared. Now we try to find the Taylor series expansion of e power of x. In Maclaurin series, e power of x is equals to 1 plus x squared divided by 2 factorial and so on. And again, for small x, we can approximate e power of x using the first two terms, which is e power of x equals to 1 plus x. After that, we substitute the approximations into the limits. Try to make it in the simplest form, and we will get minus 2 divided by 1 plus x. Lastly, we take the limit as x equals to 0, and then we got the answer. The first answer is minus 2. Now we move to the next action, which is approximating the integral using Maclaurin series. As you can see in the problem statement, there is trigonometry in it. So we will expand the cos x squared by using Maclaurin series. Just like before, we assume cos x squared as cos u. Then the Maclaurin series for cos u is equals to 1 minus u squared divided by 2 factorial plus u power of 4 divided by 4 factorial. Substitute u back to the x squared, and then we will get cos x squared equals to 1 minus x power of 4 divided by 2 plus x power of 8 divided by 24. Using the first two terms, we will get cos x squared equals to 1 minus x power of 4 divided by 2. Now we can approximate the integral. After expand the cos x squared, we can write the integral like this. After that, we will use the simple integral and combine it, and we will get 1 minus 1 over 2 times 1 over 5. And then for the final answer, we will get 9 over 10.
So now we'll explore how to stimulate electrical circuit that containing resistor, inductor, and capacitor, like what we call it as RLC circuit. And specifically, we will use the Taylor method to model how charge and current change over time in this circuit. So as what we see, we will apply this differential equation in our later example. And now the question is why we use the Taylor method. So this is because it's accurate for short time state, it's simple to implement, it's great for modeling rapid changes, and last but not least, it's efficient for short-term circuit behavior. Okay, let's look at this specific example. It's provide an image of RLC circuit, and the question asks for using second order Taylor method with step size h equal to 0.1 to approximate the charge and the current at 0.1 and 0.2. And it's also mentioned there's not external voltage source. So first thing first, we need to identify the value based on the image and the question. It's a series RLC circuit which consists of 10 ohm resistor, 1 Henry inductor, 0.1 farad capacitor, and it got mentioned the initial charge is equal to 1 and the initial current is equal to 0, and there is not external voltage source which V will equal to 0. Okay, the next step is we're going to form differential equation for the circuit. So according to the Kirchhoff law, we will form 4 equations for the first one, and the equation for the voltage of inductance, voltage of resistance, and also the voltage of capacitor. But for the last equation, we need to be alert because we need to integrate this equation to gain the voltage of capacitor. Okay, now we can substitute all equation of voltage and all the value of LRC into the first equation, and the next step is we differentiate the charge and then put the differentiation equation of charge into the equation that we formed just now. Then we will gain a differential equation, and for the differential equation we are able to derive two second ODE differential equation, which is these two. We can now start to find the value of charge for the step size, which is 0.1 second. So this is the initial condition of charge, and we need to form the first, second, third, and the fourth differentiation equation of charge, and we apply the initial condition into the equation, and we will gain the value of the charge. As we know, the step size is 0.1, and the Taylor series formula, as I showed in the slide, will be applied in later. So now we substitute all the value that we gained just now into the Taylor series, and at the end we will gain the answer of the charge is 0.9629 coulomb. To find the current, we will start with the initial condition which t equal to 0, calculate the derivative at each state. Now, use Taylor series to predict next value and repeat it for as many steps as needed, like just now how we're going to find our charge. So at the end, we will gain the answer of the current is negative 0.95 ampere. So what we can conclude for the answer that we gained just now, that means that our capacitor is discharging and charge is decreasing for 1 coulomb to 0.96 coulomb, and current start at 0 ampere and become negative. This is the discharge current, and the system will continue oscillating until the energy dissipates in the resistor. So if you want to find the charge and the current for the time at 0.2 seconds, we will just repeat the same step at how we found the charge and current in just now, but please remember the charge and the current value that we find just now will be the initial condition for them. So by using the Taylor series method with the h equal to 0.1, we will get the charge, the second charge equal to 0.8892 coulomb. So to find the second current with the initial condition t equal to 0.1 second, and the current will be the negative 0.6167. So we will calculate the derivative by step. So by using the Taylor series method, we will gain the second current with the step 0.2 will be equal to negative 0.8073 ampere. To conclude our topic, the Taylor method provides a straightforward yet accurate way to approximate solution to ODE, especially for short-term prediction with small steps, and it is partially particularly useful for modeling rapid changes in systems such as traction response in RLC circuit like this. And while powerful for short interval, its computational complexity grow with a higher order term, making less efficient for long-term simulation compared to other numerous systems. So this really make the telemeter valuable tool for engineers and scientists work with dynamic system. Thank you for your attention.